Okay, thank you for coming. Welcome. Let's talk a bit about unit tests and properties of unit test. Little disclaimer right up front. I won't be showing you any code, so I won't be talking about exactly this is how you should write unit tests, right? So this is more about, in general, about properties we want to achieve to make unit tests worth our while, to make them efficient, and to get all the things out of them that we need out of unit tests. Let me introduce myself for a second. My name is Arne Mertz. I'm working as a software engineer at Züke Engineering or at Züke Group. I've been learning and using C++ for almost two decades, almost 20 years. I say learning because, well, as you probably know, you never stop learning because there's always something new in C++ and something old you didn't know yet. Regardless, I'm a trainer for C++ and for the clean code area of topics internally at our organization, but also externally and as a freelancer. So I will not give you another definition of what a unit test is, but since we are talking about unit tests, I think we need some common understanding at least what I am talking about when I say unit test. So this is a word cloud that I gathered by looking up unit test definitions on Google. I took like the 21st definitions I came across, I put them in the word cloud generator. This is what it came up with. So obviously there is unit and test in there, so I reduced all the plurals to singulars to make it a bit more readable, to not have like units and unit and stuff like that. But what you also see is like there's software in there, but there is then module, component, function, subroutine, stuff like that in there, right? And there is like parts and pieces. What I think is important is down here the individual, isolated. So this already gives us a first hint at what unit tests are about, like having the isolated parts and testing them. Also important is automated. So those are not manual tests. Like by incidents, like you close together, written by the developer. So when I talk about unit tests, what I mean about that, and what most of these definitions agree on is unit tests are automated by the programmer, usually using some kind of unit test framework, but not necessarily. So you can write unit tests on your own, like using just asserts. But usually you want to use a unit test framework like gtests, catch, boost test, I think. I think those are the three most popular ones in C++ at least. If you're not coming from C++, there are other testing frameworks, but I think all the languages have their unit test frameworks. Unit tests cover the entire software, so not in one test, but all the tests together cover at least a huge amount of our classes, functions, and so on in our software. So we need a big coverage, and they test individual units for whatever a unit is. So the other part about this is, what is a unit? Is a small and individually and logically separated piece of code. It still doesn't say, is it a function, is it a class, something like that. It can be a function, it can be a class. Some of the definitions say it's a module or a submodule or a component. It can also be like a smaller group of classes. Think about, for example, standard containers. If you have a vector, you cannot really have a vector without using the iterators, right? Which is a different class. It belongs together. So the two classes together form a unit. There is the testing pyramid. And again, like there are a couple of different versions, but all of them have basically the unit tests in the bottom, which is the basis of the testing pyramids. Because the unit tests are the ones that go really into the details of each individual unit. And then above that we have, and the unit tests have like the broad base because they have the big coverage. And then above that we have the integration test in most cases, if you see those pyramids, not in every case. So integration tests, at least how I talk about them, are tests where you take like different units and put them together and see that they play well together. Because if you have like this class and that function and each of the functions and classes works well, that doesn't mean that they work well together. So you have to integrate them, and those are the integration tests. Typically also written by the programmer, typically also using like unit testing frameworks. And above that, we have like a plethora of different kinds of tests that have like different names depending on what kind of systems you work on, whether you're working on a single application or whether you're working on a big embedded device where you have like multiple services running in parallel. So like testing a single service, testing all the services, testing the whole device, like there's like different namings depending on which context you're in. So, but since we are not talking about that tip of the pyramid, we're talking about unit tests and maybe the distinction to integration test to make it clear where you draw the boundaries. So unit tests are one of the many tools we have in our toolbox, right? So we even have like different kinds of tests as we have just seen. So if you have like this toolbox with all the different tools, what do we use this specific tool for? Pretty obvious. What comes to mind first is quality assurance. Usually thinking about we write a new feature, we want to test this new feature to actually make sure that the new feature does what it is supposed to be doing. In this case, for units, we have a new unit, we have write a new class, write a new function. So we want to make sure that it actually does what we design it to do, or what we want it to do. What's also important is when the unit test fails, that it actually documents what's wrong. Because like running a suite of like 5,000 unit tests and then just computer says no, great. What do I do now, right? So we really want to see what is failing here, and we get to that later to what the actual documentation of failures entails. Then we have test-driven development. Who in here practices test-driven development? Sometimes, regularly. Okay. Yeah. So there are multiple definitions for test-driven development as well. Usually it goes into the direction of, well, at least test-first development. The idea is I know roughly what kind of unit or class or function I want to write. So I write the tests for that first, which basically pins down how I want it to be used. And then I compile and run the test. And of course, it doesn't compile it first, because if I have a new function and I just use a function, it doesn't exist. And the compiler says, well, the function doesn't exist. So I write the function and I make the tests green. I make that single test that I've just written, I make it green, I make it run. Then I write the next test for a different aspect of the same function or a different method of the same class and stuff like that. And I make that green again. And we have these red-green refactor cycles. I write a test, it's red. I write the necessary functionality to make it pass. And then in that kind of development, very important, the refactor part, because if I just write next test, make it green, next test, make it green, then my code gets messy really quickly. So I consciously have to go and do this refactoring to clean it up again. And typically these red-green refactor cycles are set to be in the order of minutes. So there are people that say, well, if you're really good and really quick, then you can do this in like 30 seconds. Maybe if you're working on a compiled language and maybe on a slow computer, that can be like compiling alone can take more than 30 seconds, but it shouldn't take more than 5 or 10 minutes or something like that, one cycle. So this has implications for our unit test as well, for the tests we are using here. When fixing bugs, we use unit tests, because usually we want to know that we actually have fixed the bugs. So we first want to write a test that reproduces a bug. Preferably, well, usually we start with a big feature test or something like that, that in the grand scheme of things reproduces a bug, but we try to nail it down to that single unit or to the 2 or 3 units that play together that have actually gotten the bug, where the actual behavior is hidden that is wrong. So We usually try to write a unit test for those units and to pin down the wrong behavior, or in that case, to make a test that should pass when we have fixed the bug. So this is another use case where we can use unit tests. And to make this worth our while, we usually don't want to like trying to fix a bug, and especially if it's like something complicated where we have to do multiple iterations of fixing the bug and trying again. We usually want to just run a single test case or a couple of test cases and not want to run our whole test suite, right? So we want to be able to select some of these cases. We want to be able to filter our test cases to actually only run what is important right now for bug fixes. And this selecting specific test cases is not only important for bug fixes, but also for other kinds of work. Refactoring is another use case for unit tests. Refactoring means we are changing our code without changing its actual behavior. So cleaning up code, making it more readable, changing names, maybe replacing for loops with standard algorithms, stuff like that, right? Not changing the behavior means, well, we should be running our test continuously to check that we didn't by accident change any behavior. Because if you like factor out stuff and maybe invert an if condition or invert the booleans in an if condition, it's really easy to make a mistake. And if like 2 days later you end up, something happened here, I did something wrong, well, you want to run your unit tests relatively often. So for this kind of refactoring, you want to do refactoring in relatively small steps. So you have like these feedback loops. If I say, okay, so this is a story I had in the past when I actually didn't know that, where I said, okay, we have like this very old code base and we are using these handwritten iterator classes all over the place. And those handwritten iterator classes were basically taken out of the very first edition of the Gang of Four design pattern book, which means they had like a Java interface. If there's a next, then go to get the next and then iterate, increase and stuff like that, instead of what we usually use these days in C++, plus operator and dereferencing operator and stuff like that. So those kinds of iterators would not be usable at all in standard algorithms and stuff like that. So I said, well, we have these old iterator classes all over the place. Let's just go ahead and replace them with new iterator classes. So what I did was basically I ripped apart the complete code base. I threw out all the old iterators, wrote new iterators, pieced it together again, and like 2 weeks later, I finally got to compile it. And then all the tests were broken. And it took me like 1.5 weeks more to actually debug and find out what was broken. If you do this in short loops, like let me just do a 5-minute refactoring, it compiles, this one test is broken, then you usually know what you have done in the last 5 minutes to break this specific test, right? So, and if you don't, then you can just roll back and say, okay, those 5 minutes have been wasted. But if you've done so for like 2 days or for 2 weeks, then you just don't, okay, yeah, I just throw it all away and start over where I was like last Monday. So these short cycles help in actually not waste time and in keeping track. Am I still on track? Have I broken anything? Here again, we want to have like fast unit tests for those feedback cycles. And this may be a surprise to some, at least not everybody I've talked to has considered this. Maybe not everybody agrees with this. Unit tests and tests in general can be taken to be documentation. If I have a look at my unit tests, well, those tests usually have been written by the same person who has written those functions and classes. And if I have a look at those unit tests, then I see how the author has designed or had in mind how this class and this function has to be used. I may see that elsewhere in the code base, but I also may see elsewhere in the code base how other people thought that had to be used, and it was completely different to what the author intended when designing this class. So this unit test, they show how it is intended to be used. And ideally,
Question. In some languages, so Python and Rust, you can put the tests in the documentation
Yes.
above the function. Is there anything in C++ that will find those and pull them out and run them?
So yes, I really like that. So in Python and I think in Haskell as well and stuff like that, you have like you can just put the test into the class or just inside the code or in the comments on the code, and the testing parameter just will interpret it as testing. This is not, to my knowledge, existing in C++. I don't know if doctest does this. Yes, so this may something in that direction, right? So yeah. So I get from what I gather from doctors, I have never used it, but I've just seen a bit of its documentation. It has been implemented in with that in mind to actually mimic this kind of thing to have it in the documentation. Yeah. So but therefore to actually have the test as documentation, we want to have the test co-located with the code, right? We don't want to have like very far apart and especially not in a completely different repository. So if you have the code, you want to have the documentation and the test for the code more or less at the same location. So like with these 5 use cases we had, correctness of our new features, fixing our bugs, maybe test-driven development, even if you don't practice this right now, maybe you can get the taste of it. Refactoring and documentation. What are the properties that we need our unit tests to have to actually make them work for those use cases, to make them the right tool for those use cases. So what comes now, please don't take this as me preaching any rules or stuff like that. Some of these things I will be mentioning seem to be considered best practices, but they are not rules, they are not guidelines. I don't say you have to do it like this. Take it into account. It may or may not work for you, right? These are just food for thought. Be pragmatic. Some of these things may seem, well, overly detailed and things that just don't apply to you because maybe you don't have that big a test base, or you don't have that big a code base, or things in here are not of a concern for you. So take everything I say now with a grain of salt. So we had a few of these check marks before in the use cases, right? We want to have correctness for our code, but also for our tests. Because if the tests aren't correct, then probably the code can't be correct, or we can't say whether the code is correct or not. Having correct tests, of course, improves the confidence that our code is correct as well, right? To have correct tests, don't reproduce logic. I've seen test cases and code logic where someone, well, very simplified example, imagine you write a function that says, okay, these numbers are odd and these numbers are even. And you insert a typo. So you say if I modulo 3 instead of modulo 2 is 0, then it's even, else it's odd. And then, okay, now I have to write unit tests. Well, let's just come up with a list of numbers and then I copy paste my code. If I modulo 3 is 0, then it's even, else it's odd. The unit test will be green because you just copy pasted the actual logic you are using, right? So you will get like 1 is odd, 2 is odd, 3 is even, 4 is odd. And if you don't have a second look, you will never come across this error. If you actually go ahead and say, okay, I don't reproduce my logic, I will just want to know, I will just test with known examples that my logic reproduces those examples. Then I can go ahead and say, okay, my tests now are relatively simple and I have known values, and I can just put in, well, 500 has to be even, and then see if my unit tests, if the algorithm I've used reproduces that desired behavior that I know to be true. Don't have too complex logic in there. So if there are like if and else and stuff like that in your unit tests, maybe those are just different test cases. If you boil it really down, just input constants and expect constants out of them. Don't just say, well, I have this bunch of constants, and if this constant is even, or if this constant is divisible by 5, then I want to have this behavior and that behavior. You just say, okay, so a very example for example, by Kevin and Henny, where when he talks about unit tests, is talk about whether a year is a gap year, so it has an additional day on February. It depends on whether it's divisible by 4, if it's divisible by 100, and divisible by 400, right? And he just makes different test cases for all these cases, and then you can just throw in a bunch of numbers that fit into the test case and say, and the outcome is true or false, and the outcome is this or that. And you don't need to have loops and ifs and elses and stuff like that, because, well, the more complex your unit test code gets, the more likely you are to actually build in some errors. And who is going to test the tests? Then we have this thing of gray box testing. So some people say you should be doing black box testing. Some people say you should be doing white box testing. So gray box is the thing in the middle. Black box means you just don't know anything about the inner workings of your class or function or stuff like that. You just test against the API. That's black box. White box is basically you can actually inspect everything that's inside your class. I would say go the middle way. Unit tests should not be friends, because if you have like unit tests being friends and being able to actually reach into your classes and touch member variables, only to observe member variables and stuff like that, then it makes it really hard to actually refactor your class. Because remember, we want to refactor all stuff without touching the tests, because the tests are making sure that our class, that our behavior stays the same. And if we remove a member variable or rename it or replace it with something else, and we have to touch our tests, we really run the risk that we are actually making the tests work again, because then they are wrong, because we introduce wrong behavior in the class, and at the same time we introduce wrong testing in the test cases. So test only against the interface, and the class should be fine. However, knowing the implementation of our class, we can test against edge cases inside the implementation. So this is the gray part of this gray box testing. So for example, let's say you write your own string class that has a short string optimization. So we have a small buffer in that, and if the string is smaller, then you just use a buffer, and if it's larger, then you allocate memory. If you know how large the buffer is, then you can write a test case for exactly that size of the string and for one larger, to actually make sure that in this transition from the buffer to the allocated memory, your string class really behaves the same. This is inner knowledge of the implementation, and you write test cases to make sure that these boundaries are okay, but still you don't touch and you don't actively observe the implementation details. To make sure that everything, or as much as possible, works well, we want to have code coverage, which means, well, we want to cover as much as possible. There are people out there saying we want to have 100% code coverage. If you're writing an application and you're having something, having a language like C++, I just assume that many people in here are using C++. You can't really unit test or test at all the main function. You can't cover main function with a test like this, because you just can't call it from anywhere. The only way to test the actual main function is to just compile the whole program and test the whole program, but this is not down in the unit test or integration test level, right? So you can't have 100% code coverage in many cases. There are other things that I will touch later that are not really possible or not worthwhile to actually test in that fine granularity. So go for a good enough code coverage. There are tools like SonarQube, Coverity, I don't know which else, that tell you this is your code coverage. and you should go to whatever, 95%, 98% or something like that. Don't just listen to those tools, because people will then just play the metrics, right? You have enough coverage when you have covered everything you can cover. You don't have enough coverage when the tool says, yeah, 95%, you have covered everything you need. Well, there may be gaps beyond the 95% that you can unit test, and then you should also test them to improve the confidence in the code, right? If you actually can't test something for whatever reason, think about documenting the gaps, because if there's someone going and say, well, we are at 97%, I want to go to 98% or maybe 99%, and goes through all the uncovered pieces of code and actually tries to find some way to test them, to cover them. If you tried and didn't succeed, maybe leave a comment at that section and say, I tried to cover this by this and this way, it didn't work, so maybe don't try it, maybe don't waste your time to actually try to cover this part of code. This goes especially in the direction of C++, but I think this also applies to other classes. Use strong types, don't use strings and integers everywhere. Let's say, what's a street name? A street name is a string, right? It's just a bunch of characters. Can a street name be empty? Does it make sense? So does the empty string make sense as a street name? Probably not. So if you have functionality that has to deal with addresses, with street names, should the functionality everywhere have to check for empty strings? Should it be able to deal with empty strings, or should it be just able to deal with a street name? So if you have a proper type that says this is a street name, and when constructing objects of that type, you do the actual check. Is this an empty string? Can I actually make this a street name, or is it something that is just invalid for this type? Then you have the check at one location, and you have to test that one location. If you use a string wherever you need street names, then all your classes that take that string as a street name have to check, is it empty, and have to maybe deal with the fact that it's empty. And then you have to write tests that all those classes are able to actually throw the correct error or give you the correct warning or whatever when they get past an empty street name, right? So having stronger types, having types for all your different kinds of domain objects, not only makes the design better and easier to work with, because you don't have to do all these out-of-bound checks and stuff like that everywhere, but only when constructing that actual type. It also makes the amount of testing much less, because you don't have to test for all those error cases everywhere, because they just can't happen anymore. So now I've covered the correctness part. The next property we would like to have is readability, because the first thing we had, or one of the things we had, was as documentation. But also when our test is failing, we want to see why it's failing, and we want to have readable tests, right? So all the clean code principles and stuff like that, they don't only apply to the production code, they also apply to the test code. And I see many people who say, well, this is only test code, I can just be lazy and write sloppy code in there. When you are debugging and trying to figure out why the test failed, then you are really grateful if someone has written actually readable and maintainable test code. So, well, as I said, use design principles. Have meaningful names in your test cases. If you're running your unit tests and you see test number 22 has failed, then you have to find test number 22 first and look into test number 22 to actually find out what it's testing. If you have a code that says, years that are divisible by 4 are gap years, then, and if test fails, then you actually know, okay, there's something in this specific location that actually doesn't work as the test expected to be. So you know where to look. use abstractions in code. We've heard the talk by Kate that there are lots of missing abstractions in code, that we usually write code and we just add code, and well, abstractions will be missing. And we will maybe see abstractions, and if you see abstractions also in unit test code, just factor out stuff. Factor out functions that instead of like having 30 lines to actually establish your preconditions, maybe factor them out and have only 1 or 2 lines to establish your preconditions. Fixtures are another example of this. So depending on the unit test framework you use, there are these fixture classes where you can have setup methods that do all the common setups that are needed to actually create your unit under test and supply it maybe with mocks or stubs or whatever you need, and do the proper setup to actually prepare them for the testing you're going to do. And this also includes having short test cases. So the ideal common test case would have like 3 lines of code. First line, the arrange or given part of the test, then the act part where you do the actual action that you want to test. This is, or in other terms, it's either arrange, act, assert, or it's given, when, then, right? So these 3 are basically these 2 are interchangeable, and these are the 3 lines you would ideally want to have. So don't factor out a function of 2 lines of code just to have a single line of code, but that's the idea, to have like, this is my arranging of the code to actually be able to then do the action and then assert that the action provides the required results. The asserts can be multiple asserts, but it should assert a single thing. Test one fact per test case. So let's say we test our own implementation of standard vector. A default constructed vector is empty. So I take a vector, I default construct it, and then I check that it's empty for whatever empty means. It can mean that the empty method returns true, it can mean that the 2 iterators begin and end are the same, and it can say that the size is 0. Those are all equivalent, so those could get into the same test case. Another fact is that a default constructed vector also has a capacity of 0, which has nothing to do with empty, right? We can change that fact that the capacity maybe is not 0, but 10 for our own implementation of whatever vector we want to have, but it's not the empty part. And if you're struggling to figure out a correct name for your test function, then it may be that there is multiple things that you are testing. So try to dissect them into 2 things. So test case should have 1 reason to fail because 1 fact isn't actually implemented correctly. The default constructor creating an empty container, if that one fails, there will probably be a lot of other test cases that fail because that is a basis basically for a lot of other things. But you can pick the most basic test case that has failed and see, okay, here's my point of failure. I can fix that, and then I can see whether the other test cases have been fixed as well. Focus on the unit under test. So you have something you are testing right here. Your function, your class, or something like that. Don't test all the things around it. If you have like your class and this uses another unit, and you basically have to have parts of that other unit injected into the class or given into the class as arguments, don't test those other parts. You have unit tests for those other parts in another location. So make your assertions about the class you are testing in this test case and not about all the other stuff. And please don't start to test compiler-generated members because, well, the compiler is infallible, or at least if the compiler has a bug, you have a much bigger problem. So trust that the compiler is implemented correctly. Trust that your standard library implementation is implemented correctly. Don't try to test the actual standard implementation. Don't try to test third-party libraries. If you don't trust the third-party libraries, maybe write a couple of test suites for the third-party libraries, but not in the unit test for your own code. Move those elsewhere to another test, right? So focus on what you are actually testing here, not on the dependencies. So writing test cases can be a usability check for your classes or for your functions, because if you have to write really convoluted stuff for your actual test case to do something, to test something, there may be a problem in the usability of your class or of your unit overall. Because if you have to write this convoluted code to make a simple test case work, you probably have to write the same convoluted case in your production code to actually use this unit, which means that it's more likely to contain some errors, to omit some stuff, or to make something well, more problematic than it should be. So check whether the unit under test is actually as usable as you want it to be. Test case order. So this is about reading the code. This is not about executing the tests. So we touched it a bit later. You actually want your tests to be independent and be executable in any order. So for the test execution, it doesn't matter in which order you write them into your test file. But for the reader who wants to read this documentation, that's important. They want to see that, well, if I construct an object of this type, then it has this and that property. They want to read this first before reading about this really convoluted stuff, what happens when I push twice and then remove another object and stuff like that. So have this from very basic to more complex use cases for the unit under test in that order to actually make the reader, make it possible for the reader to follow along to actually get an idea of what the test cases are testing here. Next thing, discoverability. I briefly touched that we want to be able to find our test cases. If I have a class that I don't know yet, ideally, if I want to have our tests as documentation, I want to find the test cases for that, right? So there are considerations about the test file names. They probably should contain the name of what they are actually testing. About the test file locations, where do I find them? So in C++ projects I've worked on, I've seen basically two different patterns. One was I have the test files directly beside the actual unit files. So I have my fancy class HPP, my fancy class CPP, my fancy class test CPP all in one directory, which is okay. It gets a bit crowdy because you have basically a factor of 1.5 or more of number of files in your directories, but you definitely will find them. The other way that I have seen is basically you have a source directory and then I have my subdirectories, and in there are at some point my CPP and HPP files, and you basically reproduce the same structure in a test directory. Maybe even in a test unit test and test integration test directory, where you have the same directory structure reproduced, so you can basically follow along and find the tests for your test cases. I think in Java this is pretty natural because you have like you have those directories just follow the package name path, and you just have like thing.that.unit my class, and you have test.that.unit my class and something like that. Important part about unit tests is speed. At my last employer, we had something that was labeled unit tests, and we had like two different versions that we could execute. The fast one would take 45 minutes to complete. The slow one would take like 2.5 hours or something like that. Remember the red-green refactor cycle and the actual refactoring with short feedback loops? Well, if you write 3 lines of code and then execute 45 minutes of unit tests, you won't get very far in a day, right? You probably execute those things maybe once a day, maybe just 2 or 3 times a week. So we want to make them fast, which has implications. Very rough back of the napkin estimate, right? So on a very busy day, we will make like effect, not actually write, but effect and change about 1,000 lines, maybe 10,000 lines of code if you actually get that far, then you're really fast and either really good or really sloppy. Either of the two, right? So roughly estimate of test code to production code, unit test code to production code, 1-to-1, maybe 10-to-1 if you have really big coverage of unit tests and really long unit test cases. But usually, I would say let's go with 1-to-1. I have 10 lines of code per test case, roughly. As I said, ideal would be 3 lines, but 10 lines is okay. Plus a bit of glue code, of factored out functions and stuff like that. If I have 100 to, and that together means I have like 100 to 1000 test cases to run in a day, after the day. But continuously, since I'm working continuously, I don't want to run them just at the end of the day. I want to run them in between because I don't want to roll back the last 8 hours I've worked on the stuff, right? I want to have a short feedback cycles in minutes. So depending on the language, if I factor in like maybe if 10 to 20 second compilation and stuff like that, then, and I actually want to do some work in those minutes, right? Then my tests should run in a matter of seconds. So last thing I've worked on, we had, I think, about 10,000 test cases, and they were like 20, 30 seconds. So this is a good time, I would say, for that amount of tests, which means our test cases should take amount of milliseconds. If you have test cases that take like 5 seconds, 20 seconds, then you will not get near that, right? So this is just very back of the napkin. So there may be a factor of 10, maybe a factor of 20 or something away from what's actually good, but this gives you a rough idea of how fast we want our unit tests to be. So what we want to do is, when we run our unit tests, we don't want to run into slow code because it will slow us down. Which means we will probably like to separate infrastructure stuff from our actual code that we are testing. For example, in a recent training, I was asked, yeah, I have this function that calculates some values and writes them into a file. What do you think takes most of the time of the execution of this function? Writing into the file. The function itself, it's a couple milliseconds, probably less, microseconds even. The writing into the file takes some time. And when they then have like a couple dozen test cases that test those functions, then you have like calculate a value, write it into a file, and the write into the file is really trivial, yeah, right? You probably get even past a file stream, or you open your file and then you just write a value in there, and then you have to open the file again to actually read what has been written into the file to make sure that the value is correct. If you separate those two, then you have test cases for calculating your values, which are really fast, and you have like 1 or 2 test cases for actually opening the file, writing into the file, and then seeing that what I've written in there is in the file. And usually this is like a very trivial thing to do. So in that case, for example, you just could say, okay, instead of opening the file myself and maybe having to open it again and again and again because I call the function multiple times, just pass a stream into the function. We can discuss about whether it should be a stream or something else outside, but in that case, they passed just an O stream into the function, and in production, that would be just an open file stream, right? They would open the file, have a file stream, pass it into the function, and the function then could just write into the file, done. In tests, they would just take a string stream, pass it into the function, and it all happens in memory. It doesn't really write into a file. And you can just say, okay, after the test case, what's inside my string stream? Is it the correct value? That's okay. And then in integration tests, you would have like 1 or 2 test cases where you actually use the two together, the file stream and the function, and you have the result. So these are examples how you basically extract those infrastructure parts, your database connections, your files, your networking connections, and stuff like that from your actual logic. Because what you really what's really important to test is your actual logic, because, well, writing into a file and writing into a database usually is relatively simple, and you can factor this out into the test that you maybe run once a day. Also, this infrastructure stuff is something that you probably won't touch during the whole day. So you don't need to run it like every 10 seconds or every 10 minutes or something like that. It's enough to run this once a day or once a week, the infrastructure part. But the logic we are testing, we are actually developing. This is the part we want to be testing. Which also means, so then you can say, okay, but I want to unit test this infrastructure code. That's okay. Maybe have your own infrastructure library and test that, or have your own infrastructure unit test suite that you only run once a day, which is separated from your actual logic unit tests. Or maybe you just say, okay, I don't need unit tests for those. I have my integration tests that cover those infrastructure parts perfectly. And then again, you get further away from the 100% coverage, right? Because you don't test your unit test your infrastructure code. So this is what you have to decide, what you have to figure out, what works best for your project. So incidentally, one of the unit test definitions I scanned for the word cloud in the beginning is by Michael Feathers, and where he says unit tests do not contain any calls to databases, files, networking, and system configurations and stuff like that. If you do this, you're not having a unit test, you're having a different kind of test. The KISS principle and the YAGNI principle. So KISS is keep it simple and stupid. YAGNI is you ain't gonna need it. So write really simple code to have less edge cases you have to test. Don't write code that you don't need just yet, because it may never come that you need it, and when it comes, then it comes differently than you just anticipate it, so you will have to refactor and change it anyway. And applying these principles mean that you reduce your code base, you reduce the amount of code that has to be tested, you reduce the amount of test cases because you have less edge cases and so on. Which means that, again, your test cases execute, the overall test suite executes faster. Maybe in the future the things come, but when they are necessary, then you have to deal with them, and then you have to write the test for them, right? But not right now. Next one is independence. We talked about that we want to be able to run like individual units to recheck when we're fixing bugs, maybe just a group of units and stuff like that. And we want to repeat individual test cases, especially if one has failed. We want to fix it. Is it running now? Without caring for all the other test cases around, and then just in the end run all the test cases. Because, well, even if it's only like 20, 30, 40 seconds to run all your test cases, if you run one test case, maybe even directly from your IDE, and it takes like half a second, that's much faster than waiting 20 seconds for all the thing to complete, right? So we want to be able to filter tests. So depending on the unit test framework that you have, in G-test, you have like these G-test filter equals, and you have just put part of the names with stars in there and stuff like that, where you can say just only run the unit tests that have this and that in their name. And in Catch 2, for example, you have like the ability to tag your tests, or what are these tests about. So use these kinds of things to actually be able to select subsets of your tests to run them. We want to have our tests repeatable. Who has come across a Heisenbug, which is basically you run the tests, they fail, you run the tests, they pass, you run the tests, they pass, you run the tests, they pass. Okay. Nightly build, tests have failed. Next morning, the tests pass again. These are really hard to catch things, and they can have different reasons. We want to have our test being deterministic. Very often there's something about timing involved in these kinds of tests. Like we run the tests and maybe the hardware is a bit slow because someone is making a phone call or something like that, and just 2.5 milliseconds doesn't cut it and takes just slightly longer, but it's still okay. If you have like strict checks for like we want to have like this amount of time, so we're writing unit tests, we're writing tests for functionality, not for performance. Performance testing is a whole different beast, right? Especially when you're using multi-threading, in which order things get executed in the different threads is really not deterministic. And including sleeps to make this actually work will mean that you slow down your test cases and you're back to fast execution again. Don't try this. So I've seen people say, well, don't use threading at all in your unit tests. Well, when the part you're working on is all about dispatching different threads and so on, that's really hard to do because, well, the logic you're actually writing you can't test. Yes.
For independence, one of the other things, the order of the test should matter.
Yes. So the order of the
If
test
you
should
don't
matter.
have the
Yeah.
order of the test,
Yeah.
your test order doesn't matter, then
Yeah.
you probably won't have to deal with at least as many sleeps to keep the things.
Yes. So if you have different tests, then the test order shouldn't matter. But even like having different things happening inside the same test, if you just say, I want this and that to be happening in that order, it usually breaks down into, well, I have to wait for this event, then I have to wait for that event, and maybe I have to put in sleeps to actually be able to wait because, well, so timing issues are really hard to actually test well and test fast, for example, especially. Yes. So you want to test the actual well, the logic and not the timing behavior because, well, you will have to run stress tests to actually make sure that the threading and stuff like that works correctly, and usually this also contains having a look at your tests and having a look at your code to actually see that there are no race conditions. Because it's really hard to actually prove whether you have race conditions or not. So this is a kind of thing that maybe you don't want to test in the unit tests that you run on several times per hour. This also includes avoiding global state. Most of tests that I've seen failing when executed isolated was due to global state. Global state can be like tied to some global variable, maybe tied to a database or something like that, which we said is out of the question anyway. But having global state means that maybe your unit under test in the first test case writes something into the global state, and your unit under test in the second test case reads from the global state and expects the previously written value because you have arranged the test cases like that. And then when you just execute the second unit in isolation, then it won't find the previously written value in there, and you will basically have tied your the test cases to each other. So this is really hard to find out what you're actually doing in your global states, besides being hard to actually reason about when writing your code, right? Because you usually want to have the interactions of different parts of the code base obvious, and like sending hidden messages via some global variable that you don't see directly is anything but obvious. So like keep that in mind. So this is also why singletons are so well discouraged these days, because, well, if you have global state, it gets hard to reason about. It gets hard to actually break things apart and test them in isolation. This also includes test cases. I have people seen writing static variables in their fixture files, which means you had to execute all the test cases in a specific order because that global would be changed by the test cases themselves. And the test cases would fail when executed in isolation for no bad reason about the actual tested code, but for bad reasons about the test code itself. So how can we decouple? Well, usually what we use is dependency injection. Sometimes we have like other ways to actually decouple things, but the most often used is, well, different kinds of dependency injection. You can do this as compile time at runtime with virtual stuff, with templating, whatever means are at hand to actually create stuff outside and inject them into your unit under test. You can use this for mocking, for example, for just stubbing stuff, so you don't have to actually use a concrete database, but you can just write a database mock and use that one. And with mocks, you can also trace like how does my unit under test interact with the other stuff that I've given the unit, right? And that's about it. Are there comments, questions? Yes.
Back when you were talking about strong types,
Yes.
one of the things that I've run across a lot is people write unit tests for, including myself, I've done it as well, for just the good case.
Yeah.
And that's not sufficient. You also want your unit test to test your failure cases.
Yes.
And that's part of the strong typing. That's part of the correctness.
Yeah.
All of that. I mean, you alluded to can I accept an empty string? Can I accept a null? What happens when I pass a null into this?
Yeah.
Yeah. You want your unit test to test you've got a valid state.
Yeah. So, well, you're testing the error cases, testing the edge cases should be included also for the coverage, right? So if you have close to 100% coverage and you don't test the edge cases, the error cases, then this means you don't actually handle those error cases, because if you did, then you would have like uncovered code in there, and you would hopefully, when using coverage tools and stuff like that, you won't find them quickly. You had the question. Thank you.
The food chain and functional benefits, but massive amounts of things that you there's just one thing that's not directed towards you, but it's just a thought. Sometimes I think the term unit tests can be a little bit harmful sometimes. I can just give an example that sometimes when you're testing some image recognition stuff, and you're basically unit test frameworks give you the possibility to fake a bunch of machine sensor input
that
I couldn't ever actually do on a real machine. And it's really the best tool in that case is unit test framework.
Yeah.
And sometimes I think people don't write that test because I don't have a test instrumentation to get control of that on that machine, and then the developers working close to the code maybe think, oh, that's not a unit test. That's not my responsibility.
So in that regard, I would say the term unit test framework is the one that's harmful here. So having unit tests is okay, but labeling something that is not only used for unit tests or not only usable for unit tests, naming that only unit test framework basically makes its scope smaller than it should be. As I said in the beginning, the integration tests are usually written by developers as well, and usually also in the same language, where you just put multiple units together and check how they work together. So integration tests are written using unit test frameworks, and there are so many use cases for unit test framework way outside unit testing itself that actually is, yeah. Yes. First. Yeah. Yes. So the comment was running test cases in different processes to actually discover these interactions with the global variables, right? Which means you just basically have as your dependency not the global variable be the specific value left by the last test case, but just being the global variable having like the initial value. And shuffling the test will basically will show that actually they depend on that value, and that the previous test cases may or may not have changed this. But dealing with shuffled test cases when you are in that situations where everything is depending on globals is really a pain in the butt, because so Yeah.
So you can just bite it down.
Yeah. So my experience with shuffling tests has been basically we had like spurious test case failures every 2 months or something like that, because that one test case that actually changed that global variable where the other test case was depending on was sometimes shuffled before that other test case and sometimes shuffled behind that other test case. And like finding then the concrete, so basically what it boiled down to was we rearranged our test cases, we switched off the shuffling and then executed them in that exact order to be able to actually reproduce where did this test case failure come from, right? So it can be hard to actually find. Yeah.
This can be handled by tool. Like, for example, TechTown, which you promoted in tools. When you remove the test case and you keep the seed from the shuffle.
Yeah, okay, when you keep the seed from the shuffle, yeah, then yeah, definitely.
Start looking out mistakes until you find the neighborhood.
Yeah, yeah,
And then
yeah. Thanks. I think Björn was first.
Yeah, I was wondering about your opinion. I fairly often write data structures, and I always feel uncomfortable writing unit tests for them because the general wisdom seems to be that you test the observable behavior from the outside. But if, say, I'm writing a red-black tree, just to take an example that everybody knows, I really want to ensure that I'm getting the rebalancing and the rotation of the internal nodes correct, because that's an extremely important part of what a red-black tree is. But it's not something that is usually visible from the outside. So what is your take on how to write tests for that?
So if you have like testing the inner workings of the data structure that you're writing. So one option would be to have like the parts of the data structure, like in this case the red-black tree, like having the individual nodes being public and having the algorithm that is actually there for balancing the stuff, making it separate from the actual data structure itself. So the data structure just say, I have a set of nodes, I have this algorithm, I throw them together, I see what comes out. And then you can write unit tests that doesn't employ the data structure itself, but employs a set of nodes, employs the algorithm, throw them together, see what comes out. And then you can do this kind of testing. So externalizing your implementation details to actually have them separate and have them tested can be an option for that. But I agree this is basically more or less a gray area, because then you would say at some point, well, I'm externalizing everything and my data structure just ties all these details together, right? There was some comment in the back row. Yeah.
Could you claim that you're doing TDD if you don't have 100% test coverage?
Sorry?
You can't have 100% code coverage and say you're doing TDD.
100% code coverage. I don't think I got the question. You can't say you have 100% code coverage and saying you're TDD. If you're doing TDD, you will have always 100% code coverage. Yes, because you only write code that actually matches those tests. There are arguments, even by someone as famous for TDD as Kent Beck, that the set of tests that you write for while doing test-driven development is not enough. So you will even probably need more tests. And yes, there will be parts in your code that you can't test, where you can say, okay, this part I can't do test-driven because if you have, like, for example, I can't really simulate a network failure or something like that. I just have to write the code that hopefully catches the network failure, but I never can test it, at least not at this level. So there are these points where you can say, okay, but now I have these. Usually those are error conditions and stuff like conditions that you really can't reproduce in the lab or in the test environment, where you have to say, okay, I do have to do this part even though I don't know how to actually reproduce this. And this is basically a part where you can, as I mentioned earlier, say, here's a comment, this is not covered by the test for this and that reason because I just couldn't reproduce it. So this is also not written in a test-driven development environment. Sorry? when you introduce doubles, because you can't say when it's none and stuff like that. Yeah. Yeah, yeah.
One other thing about TDD is only good as the requirements that you test, right? So if you don't write your test to test the failure conditions, well, you're just testing the accepted, the good path. Not very good TDD.
Yeah.
Still, I've seen TDD fail to have 100% test coverage for just that reason.
Yeah. So in one of my classes, I basically I go and say, let's build a stack class and let's build a test driven, and these are the requirements for the test class. And then you say, well, if you take top or pop from an empty stack, it's not specified, but what will happen, right? And then people go ahead and say, well, I check if it's empty and then I throw an exception, or if I just have top, it just has to return some value, so I just change the signature to return an optional or something like that. And some people say, well, it's not specified, so I can just base it on a standard vector, and if you use pop or pop back or back on an empty standard vector, it's just undefined behavior. That's okay because there's no specification for this part, yeah. But you have to maybe then leave a comment or something like that. But yeah, there are these gray areas that you really have to figure out how you want to cover them, or if you leave them uncovered. More comments? Great. Thank you very much.